Good evening, students. Today's class highlights. Once again, I am making this video. So today we have solved two problems. Before this class, all of you have seen armature winding design or stator winding design. So related to that design part, these problems have been studied. Problem number 1. Determine a suitable number of slots and conductors per slot for the stator winding of 3-phase 3300 volts 50 Hz 300 rpm alternator. The diameter is 2.3 meter and armature core length is 0.35 meter. The maximum flux density in the air gap should be 0.9 Webers per meter square. Assume sinusoidal flux distribution. Use single layer winding and star connection for the winding. So this is given problem. All of you note down the given data with respective symbols. With respect to symbols, what are the things have been given with symbol? Okay, you write down. So as usual, we start. Number 1, synchronous speed. Synchronous speed is given in revolutions per minute. First you convert into revolutions per second. 300 by 60, 5 rps. So this synchronous speed is also equal to 2f by p. By using this equation, you design number of poles. P equal to 2f by ns. So we are going to get number of poles equal to 20. Maximum flux density is given 0.9 Webers per meter square. Hence, it is possible to calculate B average flux density in air gap, that is 2 by 5 into Bm. You substitute the value, then B average, finally we are going to get 0.574 Webers per meter square. Then after calculation of B average, go for flux per pole. Flux per pole equal to B average pole pitch into length. P average is 0.574, pole pitch is pi d by P into length. Substitute all the respective values. So flux per pole equal to 72.5 into 10 to the power of minus 3 Webers. Voltage per phase voltage. So given voltage in the problem is line voltage. Hence we have to determine phase voltage because alternators are always star connected. For star connected, EP equal to EL by root 3. So you substitute value, finally we are going to get EP as 1910 volts. So this phase voltage is also equal to 4.44 F phi Tp into kW. By using this expression, you have to determine number of turns per phase. So you can assume winding factor as 0.955 or 0.96. So finally we are going to get turns per phase, that is around 124. So next, the slot pitch should be nearly 40 mm. The slot pitch should be nearly 40 mm for 3.3 kV machine. It is already known in previous section discussion. The slot pitch varies the rating of machine, voltage rating of machine. So for 3.3 kV machine, the slot pitch may be nearly 40 mm, one condition. Hence, we have to determine slots per pole per phase, Q. This Q equal to pi d divided by 3 P into Is, where P is number of poles, Is is slot pitch. Here one thing, the diameter D and slot pitch should be of same units. Now in this problem, D is expressed as 230 centimeter, Is is taken as 4 centimeter. Either you keep D equal to 2.3 meters, Is should be also convert 40 into 10 to the power of minus 3. You understand very thoroughly. D and Ys should be of same unit. So finally Q we are going to get as 3. We have to use single layer winding, therefore an integral number of slots per pole per phase has to be employed. Hence total stator slots should be equal to 3 times of P into Q. Slots per pole per phase. To slots, what are the divisible factors? Multiply. Number 1 pole, number 2 phase. So 3 times of PQ. Substitute the values, we are going to get as 180. Number of stator conductors should be equal to 6 times of TP, where TP is turns per phase. We are going to get as 744. Hence finally conductors per slot, that should be equal to total conductors divided by total slots. We are going to get this value as 4. Therefore total stator conductors used 180 into 4. 180 number of slots into conductors per slot. 720 we are going to get. Turns per phase used divided by 720 divided by 6. We are going to get as 120. Thus there will be a change about 3% as the turns per phase used are 120 instead of 120 calculated value of 124. Hence finally we are going to get some adjustable value near to first calculated. Final value is 120. Problem number 2. A 1000 kVA 3300 volts 300 rpm 3-phase alternator has 180 slots with 5 conductors per slot. Single layer winding with full pitch coils is used. The winding is star connected with one circuit per phase. Determine the specific electric and magnetic loadings. If stator bore is 2 meter and core length is 0.4 meter, using the same loading, determine the corresponding data for 1250 kVA 3300 volts 50 Hz 250 rpm 3-phase star connected alternator having 2 circuits per phase. The machine have 60-degree spread. So this question is asked number of time in VTU examination for 10 marks, minimum 10 marks. So first you understand the problem. Then procedure becomes very simple. Here it is a combination of two problems. First case alternator is 1000 kVA. Second case alternator is 1250 kVA. So first what he asked, all data is given related to 1000 kVA. Determine specific electric and magnetic loadings. It is the first part. After that he has given one more condition. For calculation of 1250 kVA, use this 1000 kVA specific magnetic loading and specific electric loading values for 1250 kVA alternator also. Remember, problem is complicated, but if you are understood very well, then problem becomes easy. Getting the idea? First case you have to calculate B average and AC. That B average and AC remains the same for second alternator. That's all. So start the answer, start the solving. First condition, we have to select 1000 kVA generator or alternator. Total conductors calculate. It is equal to total number of slots into conductors per slot. So data related to 1000 kVA, that is 180 into 5, 900. Turns per phase, total conductors divided by 6. So we are going to get as 150. Then synchronous speed, Ns equal to 300 rpm divided by 60, 5 rps. This synchronous speed is also equal to 2f by p. Go for calculation of number of poles, p equal to 2 times f divided by ns. So finally we are going to get 20. The slots per pole per phase, q equal to total number of slots divided by number of phases into number of poles. So we are going to get q equal to 3. Distribution factor, angle of spread is given. Angle of spread is given. In general, kd equal to sin theta by 2 q into sin theta divided by 2 times of q. General expression. It is also available in previous problems, induction motor problem. So q equal to 3, angle of spread theta equal to 60. Substitute the value, go for 0.96. Then slots condition is not given. Angle of chording or short pitch winding is not given any condition. Hence, we have to assume coils are full pitched. Hence, winding factor equal to Kp into Kd. So finally, winding factor equal to 0.96. Then voltage per phase. Given voltage is line voltage. Always alternators are star connected. Go for phase voltage 1910 volts. Next, you advance for the calculation of flux per pole. Ep divided by 4.44 f Tp into Kw. That is, Kw is winding factor. So you substitute the value, flux value we are going to get as 59.8 into 10 to the power of minus 3 webers. Then you calculate pole pitch. Pole pitch equal to pi d by p. Pi d by p, that we are going to get as 0.314. Area of pole equal to pole pitch into L. We are going to get 125.6 into 10 to the power of minus 3 meter square. Then specific magnetic loading, B average equal to flux per pole divided by area of pole. So you substitute B average equal to 0.476 webers per meter square. One data we found. There is only one phase in first part for 1000 kVA alternator. There is only one phase is given. Hence, one phase means one circuit or number of parallel path, A equal to 1. Hence, current through the conductor equal to phase current. Getting the idea? So, therefore, current per phase equal to kVA rating in volt ampere divided by phase voltage. So, Q into 1000 divided by 3. This is kVA rating in volt ampere per phase. Then to EP, phase voltage. So, we are going to get as 175 ampere. Therefore, specific electric loading AC equal to 6 times of Iz into Tp divided by pi d. Why you are taken 6 times of Tp? What is the AC? Specific electric loading in general, AC equal to Iz into Z divided by pi d. So, Z, total number of conductors, equal to 6 times of turns per phase. Understand? Z equal to 6 times of turns per phase. So, you substitute value. So, we are going to get as 25,000 ampere conductors per meter. Then you determine peripheral speed. Peripheral speed VA equal to pi d into Ns. So, we are going to get as 31.4 meters per second. Now, this is first part of the problem is over. So, now you have to go for what is given condition. This specific magnetic loading and electric loading remains the same for next alternator, sir. So for 1250 kVA generator, start again. Ns equal to 250 RPM is given. This is for data of 1250 kVA generator you take. So it becomes 4.16 RPS. Number of poles 24. Again assume winding factor as 0.96. Determine output coefficient as usual. C0 equal to 11 times of kW B average AC into 10 to the power of minus 3. You substitute value directly, we are going to get as 126. So from output equation, Q equal to C0 D square L Ns for AC machine. Therefore D square L equal to Q divided by C0 Ns. So we are going to get as 2.39 meter cube. You call the equation 1. Keeping the same peripheral speed as the previous case. So keeping the same peripheral speed, pi d into Ns equal to 31.4. So here change is Ns, same peripheral speed, but Ns changes for second machine. Ns you substitute of second one, then we are going to get as the diameter 2.4 meter. Then go to the equation 1, get the L equal to 0.41 meters. Then pole pitch equal to pi d by P. Substitute all the values, we are going to get as 0.314 meters. Flux per pole equal to B average into pole pitch into D. Here it is a small mistake, you can take B average into pole pitch, it is not D, you make as L. In previous machine 1 it is available, it is not D, it is L. So you substitute values, you are going to get as 62 into 10 to the power of minus 3 Webers. So given that number of parallel paths for this generator, alternator, 2 circuits are given, that is number of parallel paths becomes 2, small a becomes 2. If number of parallel paths are given, then EP, you use this expression, EP equal to 4.44 TP by A 5 into kW volts. If number of parallel paths are given, TP by A, you have to make the correction. Okay. Therefore, TP equal to develop the expression. So we are going to get as 289. Total conductors equal to 6 times of turns per phase. We are going to get 1734. Then total slots equal to 3 times of poles into Q. So we are going to get as 216. Then conductors per slot equal to total conductors divided by total slots. We are going to get as 8.03. That value we can take integer only. It should be 8 conductors per slot is modified. As per this value, again total conductors equal to multiply 1728. Then final turns per phase as per this new conductors, total conductors divided by 6. 1728 divided by 6, 288. Hence, this problem has been asked a number of times. Friends, you have to prepare, try to understand. Thank you to one and all.